Two of the most successful theories ever written contradict each other completely. General relativity describes spacetime as smooth, continuous, bending gracefully under gravity like a stretched sheet. Quantum mechanics describes reality at the smallest scales as grainy, probabilistic, and fundamentally uncertain. Both theories work extraordinarily well within their own domains. Put them together, and the mathematics breaks down entirely. This contradiction is one of the deepest unresolved paradoxes in all of physics, and in January 2026, researchers finally built a roadmap that could let us test which picture of reality is actually correct. Decades ago, physicist John Wheeler proposed something genuinely strange to try to resolve this contradiction. He suggested that space-time itself might not be perfectly smooth after all, that if you could somehow zoom in far enough, down to scales almost unimaginably small, space-time might reveal itself as something closer to a churning, bubbling foam, constantly fluctuating in tiny random ways. He called it quantum foam. For decades, it remained a fascinating idea with no clear way to actually test it because these fluctuations, if real, would be almost impossibly subtle. Here's the deeper problem that kept the idea stuck as pure speculation. Different theories attempting to unite quantum mechanics and gravity predict very different kinds of space-time fluctuations, different patterns, different strengths, different behaviors. Without knowing exactly what signal to search for, experimentalists had no real target, no way to point their instruments, and know what a positive result would even look like. In January 2026, a team led by physicist Sharmila Balamurugan at the University of Warwick, working with researchers at Caltech, published the first unified framework solving exactly that problem. Rather than treating each competing quantum gravity theory separately, the team organized every major proposed type of space-time fluctuation into distinct categories based on how those fluctuations should behave mathematically, and worked out precisely what measurable signature each category would leave behind inside a laser interferometer, the extremely sensitive instruments already used to detect gravitational waves. That last detail matters enormously. This isn't a proposal requiring some entirely new piece of technology that doesn't exist yet. The framework applies directly to instruments we already have, including LIGO, the same detector that first confirmed gravitational waves in 2010, and it applies to new purpose-built experiments currently under construction, including one called QUEST at Cardiff University and another called GQuEST at Caltech. GQuEST in particular uses a clever new technique called photon counting interferometry, precisely counting individual photons produced by potential space-time fluctuations while filtering out ordinary background noise. According to the researchers behind it, this method could detect a genuine quantum gravity signal up to 100 times faster than a conventional interferometer setup. And crucially, the experiment is designed to give a clean answer either way. If the predicted signal appears, it would represent the first direct experimental evidence for quantum gravity ever recorded. If it doesn't appear, it would rule out an entire range of competing theories, narrowing the search significantly, which is nearly as valuable scientifically as a positive detection. Professor Animesh Datta, one of the researchers behind the framework, described the significance plainly. With this methodology, physicists can finally treat every proposed model of space-time fluctuation in a consistent, directly comparable way, and use it to design smarter experiments capable of confirming or ruling out specific theories of quantum gravity one at a time for the first time in a systematic manner. There's an unexpected bonus buried inside this framework too. The same detection methods being refined to search for quantum gravity signals turn out to be useful for two other major open mysteries as well: searching for a stochastic background of gravitational waves rippling through the universe, and searching for subtle signatures that dark matter itself might leave behind in exactly this kind of extremely sensitive measurement. To be properly honest about where this stands, this isn't a discovery yet. It's a precise, carefully constructed roadmap, the first of its kind, telling experimentalists exactly where to look and what a real signal should look like once next-generation detectors come fully online in the years ahead. But after decades of an idea sitting purely in the realm of speculation, physicists now have, for the first time, a genuine, testable path toward answering one of the oldest open questions, connecting the very small to the very large, whether the fabric of space-time itself is smooth or secretly, subtly made of something far stranger. What do you think? Is space-time perfectly smooth all the way down, or is Wheeler's decades-old idea of a bubbling quantum foam about to be confirmed? Let me know in the comments. Subscribe, because next time we are covering HD 1T9733b, a planet where the wind blows sideways at thousands of miles an hour, carrying rain made of molten glass.